Good afternoon, everybody. Welcome to this week's DeFord. We're very happy to have our very own from the JSG, Demian Saffer, here today to talk to us. Doesn't really need much introduction, but Danny's going to introduce him anyway in just a second. I will hand over to Danny to tell us who this person is.
All right, yeah, just in case you haven't met Demian. So it's my pleasure to have you here, and I think even though he's one of our own, I think often we don't get the accolades we deserve within our own schools. We go outside and give talks and so forth. So I think I'm super happy that Demian agreed to give this lecture, which has a little bit of history. He was the 2022 HEU Birch Lecturer, and I've heard lots of great things about his talk, even though I was not at the super spreader event in Chicago. And so we figured, I think, it'd be fantastic to have him here. So Demian is a professor in the department. He's the Scott Petty Endowed Chair. He's also the director of UTIC, the Institute for Geophysics, since 2019. His research interests are largely in subduction zones, but really in active tectonics, mainly subduction zones, subsea floor instrumentation, geomechanics, role of fluids in faulting, and just overall, fluid flow, solute transport, and heat transport. So rocks and water, good, not ice. So that's his talk was supposed to be last week, but it was not liquid enough. So the water. So it's this week. He has written lots of papers, over 120, according to his website. His work has been cited over 10,000 times. He has been, and this is really pretty impressive, or very impressive to me, he's been on 11 IODP cruises. I've heard he's been helicoptered off a couple of times, but he's been either the chief or the co-chief on 5 expeditions, which is really quite amazing. It's a lot of time at sea, more than I probably would care to be at sea. He got his BA from Williams College. He is a bona fide banana slug. Doesn't look like it, but yeah. So he got his PhD in 1999 from UC Santa Cruz. He was an assistant professor for 3 years at Wyoming before moving to Penn State. Probably heard of this place. He was an assistant professor, associate professor, full professor, and eventually the head of the Department of Penn State until 2019, before we were able to lure him away. Part of that romance started when he was a visiting professor at UTIC in 2015-16. So he has, sorry, it's going to take a while, but as I said, he has done a lot of things, a lot of IODP-related things. He's been a leader in the community when it comes to subduction zones, SC4D right now, geoprisms. He and I actually met in 2010. We were both on the Margins Steering Committee and writing the decadal report. Both of us probably wouldn't have blocked that out, but we were basically incarcerated for a week at NSF writing a decadal report. That was fun. But he was the 2005 Donath Medal recipient, very prestigious. He was the 2019 Friedrich Wilhelm Bessel award winner from the Humboldt Foundation. And as I said, he's the 2022 HEU Bird Lecturer. And that's really what sort of like motivated my invitation to him. Not that I didn't think he would do great otherwise. But so with really no further ado, I'm very excited about this. And thanks very much for doing this, Demian.
Mic up here. All right. I'll just say I think it's funny that you both said you were happy that I was giving a talk before I even gave the talk. So it's okay if you change your mind. No, thank you, Danny, for that intro, and thanks for inviting me. There we go, some mood lighting. So, so Danny had sort of contacted me and said, hey, you gave this HEU lecture, the Birch lecture. Would you want to give something similar or give that talk here? And I thought, well, that talk was a little bit too focused, in my view, on just tectonics and tectonophysics in a way. And so I wanted to back up a little bit. And so this is a similar talk, but not an identical talk. So for those of you who may have attended that talk, hopefully this won't be too much repeat. Or if it is, maybe you'll understand me this time, since I'm sure I rushed through it too much at the time at AGU. So what I'm going to talk about today is, I've called it wiring the megathrust. And what I'm going to talk about is recurring and triggered slow slip events, which are a form of fault failure, basically slow motion earthquakes, that occur all the way out near the trench in the subduction zone. And so part of this talk is about the instrumentation that allows us to access this region and with really high precision measure things that 10 years ago we would have thought were almost impossible to do. And then there are, of course, important implications for hazards and earthquake physics in general that come out of this. And so this is a kind of a 3D cutaway. This is actually a seismic data collected by Nathan Bangs and others. So it's a UT data set, UT-centered data set that was collected in 2006, 2007. And what's shown here is this is the plate boundary right here. This is a time section, not a depth section, and so that's just why the geometry looks a tiny bit wonky. So here's the subducting plate. This is the upper plate, primarily formed of bulldozed or off-scraped sediments from the oceanic plate. And all of these lines here are actual boreholes that have been drilled into the system as part of a major IODP integrated ocean drilling program, now International Ocean Discovery Program. They keep changing the name to keep it fresh. A series of expeditions over the last decade. And the red line on here is actually a cabled network that provides real-time data back to the shore in Japan. That's used for early warning and also for real-time data to study earthquakes, tsunamis, and that kind of thing. The yellow dots are ocean bottom sensors like OBSs, so ocean bottom seismometers and pressure gauges. And then there are sensors in some of the boreholes that I'll talk about that are also wired into this. So truly wiring the megathrust. And if you wanted to, after this talk, I can show you how to get onto a data portal where we can actually look at some of the data from these boreholes in real time across the Pacific Ocean right now. Kind of cool. Actually, what's really cool is at one point I was on a plane and I paid whatever it is, $400 for the internet on the plane, and then I was on the plane 6 miles above ground looking at real-time data from these boreholes off Japan that were 3 miles underwater, and I thought that was like the coolest thing, so I had to put it on Facebook. None of my friends thought it was that cool. All right, so what do these observatories look like in the boreholes? This is just some kind of eye candy. This is a view of one of the wellheads kind of looking down from above as it's being lowered from the drill ship into the ocean. It'll be lowered down through a few kilometers of ocean and then latched on to the top of an installation at the seabed. And so you get the sense that these are not small, right? When you think about a wellhead or a well, you might be thinking about a water well on land. Multiply that by about 30. And then this is another example of some of the instrumentation that we put down. This is what it looks like when you're trying to get it into the borehole from the surface using a camera to guide you and the ship's thrusters. And so you kind of could imagine, I don't want to spend too much time on this, but it's, again, fascinating to me. You could imagine being at sea level on a boat, and then you're lowering a pipe that's made of steel, but actually at the length and the diameter that you have for steel, it's really like a cooked piece of very thin spaghetti, maybe even thinner than that, more like a human hair or somewhere between the two, and you're lowering that down and trying to fit it through the head of a needle on the floor from your waist. That's approximate scale here. And the engineers and the captain of the ship are able to do this fairly routinely. And it only takes, okay, for me doing that with the spaghetti and the needle would be infuriating, especially if it took 20 minutes or half an hour. But that's fast when you're doing this kind of operation, and they're able to do it pretty routinely and successfully. So it's kind of amazing. All right. So in terms of, one of the things that's made this a really exciting topic is that there's been a real evolution of thought in terms of how we view subduction zone earthquakes. So this is now a 25, almost 26-year-old cartoon that shows this idea of, cross-section of a subduction zone. And what people have thought for a very long time is that you have essentially sort of soft, unconsolidated material that's not lithified near the trench that just creeps along stably because it can't hold stress, it can't accumulate stress, it can't lock up. Then you have what's called the seismogenic zone, and then beneath that, because of either hydration of the mantle or increasing temperature that brings you across the brittle ductile transition, you again have something that would behave ductily and can't have earthquakes. And so the idea is you have a seismogenic zone where great earthquakes occur, and that's flanked by zones where creep occurs. As we have more and more observations, we have found a lot of more interesting behaviors, and that includes slow earthquakes and tremor that seem, again, to flank this seismogenic zone, but in some cases also occur within it. And then more modern observations with denser instrumentation and also just better seismological data have shown us that this is actually a really heterogeneous and kind of patchy interface between the plates. And so the idea is that it's far more complicated than we had thought it was. And in particular, it's both patchy in space and also exhibits not just either stable creep, sort of peaceful aseismic creep, or earthquakes, but a whole spectrum of things in between. And so this spectrum of slip behaviors in particular has emerged as a really fundamental question, because if faults can behave in ways where they can creep along peacefully, or they could lock up and then slip a little bit, kind of like a slipping clutch in a car, which may be an analogy that only people born before 1978 understand in this audience, but right, all the way spanning from that to something like that looks like an earthquake, but it's got a lot of low frequency energy, all the way to something like a regular earthquake. This whole spectrum tells us that the physics of faults are much more complicated than just a simple threshold where it's either stable or unstable. And so there's a window here that we can take advantage of to understand the fundamental physics of faulting and earthquakes. Danny mentioned this SZ4D, or Subduction Zones in 4 Dimensions program. It's really an initiative that's in its nascent phases. It's likely to be the next kind of decadal to multi-decadal major international program to study subduction zone hazards. And some of the big questions about subduction zone earthquakes that are posed in this science plan are exactly the kinds of things we're trying to tackle. What controls the speed and mode of slip? In other words, what is it? What are the underlying controls on this spectrum of slip behavior? And then a very specific kind of hazards-focused question is, what is the potential for seafloor displacement and significant tsunami generation, which really speaks to the question of, is there going to be slip all the way out to the trench where you can displace the seafloor? And of course, this is also motivated, well, not just by recent events, as I'm sure many of you know about the tragic events that we're hearing about now in Turkey and Syria. That's an example of a shallow rupture, right? And so that has an amplified effect. In that case, it's because it's near population centers. In the ocean case, shallow rupture gives you a much higher probability of a tsunami. And again, this is because the displacement's happening at the seafloor, and you're actually able to very efficiently displace the seafloor. So here's an example from the Tohoku earthquake, which I'm sure folks here have heard about and remember. It was a magnitude 9 earthquake. What was kind of, at the time, thought to be anomalous about this earthquake is that the highest slip was actually near the trench. And we're talking 50 plus meters. Some models have it at 60 meters of slip near the trench. So it's not just that it was large slip, but it was also focused at very shallow depths. And what's shown here is just an example. This is a data set of differential bathymetry. So this event was so large that actually taking essentially topographic maps of the seafloor and subtracting them from one another from post-2011 to pre-2011 can actually image, and that's kind of what's shown in red here, image that focused displacement, the vertical displacement of the seafloor. And so this is the 2011 post-earthquake minus pre-earthquake. This is post-earthquake minus earlier pre-earthquake, and this is the two earlier differenced. And you can see this clearly is demonstrating significant bump in the seafloor. So it's huge, right? And of course, we all know that generated a widespread, devastating, and very large tsunami. The other sort of side of the coin is if it's not yet broken, then we might want to be able to go assess whether it's locked up and has the potential to break in an earthquake. So what's shown here are two different locking models that are equally able to honor existing data for Cascadia. And so red is something that's completely locked, and as you go to cooler colors, that means that it's less locked up. It's essentially a lower percentage locking. It's based primarily on onshore geodetic data, GPS data, but what it shows is that we can't tell the difference with the data we have. Even with a dense network of instruments on land, we cannot tell the difference between something that's basically fully locked up at the trench, in which case the next magnitude 8 plus or 9 earthquake would break through that very effectively, or something that's creeping at the trench and we just can't see it because it's invisible from our vantage point. Okay. So what I'm going to talk about today is a relatively new way to think about offshore geodesy that's got incredible high resolution. And I kind of gave you a hint of what that is. It's these borehole observatories. I'll kind of show you how these work and why they're so good. Talk a little bit about, really the meat of the talk is actually talking about what we see with these offshore Japan, and we're detecting these slow earthquakes or slow slip events, and we think we actually have enough information to talk about where they occur, not just somewhere out there, when, and of course how big they are, how much slip they take up. And then if I have time, I'll kind of talk about what else we know about the habitat of these events, and sort of why they happen, and what may be controlling their slowness as opposed to failing in a big regular earthquake. Okay, So this is the sort of geologic setting here. So this is Japan, where the Philippines, we're in the sort of southern half of Japan off of Honshu, where the Philippine sea plate is subducting beneath the Eurasian plate. And what's shown here in the blow up is contours of slip in the last great earthquake in this region. So this was 1944. It was a magnitude 8 class earthquake. This is the hypocenter, and then these are contours of slip labeled as such. This is that cabled network that I showed before. These are those nodes which have ocean bottom seismometers and pressure gauges. The boreholes that I'll be talking about today are two installations, the triangles, the blue one and the red one. And I'll make reference to a third one that's not on this map yet because it was only recently installed a few years ago, right out near the trench. Just for reference, this little star here is a magnitude 6 earthquake that occurred on April Fool's Day in 2016. Actually, while I was here as a visiting professor on sabbatical, I went to see because apparently I went to see a lot. And I'll talk about this because it's a good calibration exercise for our boreholes because it's a relatively small event and it's well characterized. This is one of the thrusters on the drill ship that we use just to give a sense for scale. And then this is the Chikyu, the drill ship, that we use to do these installations. Okay, and in cross section, this is where those installations lie. So here again, this is a seismic section. Here's the plate interface, tracing with the laser pointer. There's subducted sediments below that. Everything above it is essentially the crumpled up thrust belt that's bulldozed forward, and then this is the igneous ocean crust down here. So we have one borehole that goes through this basin fill and into the top of this accreted sediment, what we call the accretionary prism here, and then another borehole here where we have sensors at the depths of these circles. And then I mentioned there's this third site out here where we also now have a more recent installation. I'll show you a tiny bit of data from that today, but that's work that grad student Josh Edgington is a PhD student here, is actually kind of still actively working on. So you can hear from him maybe sometime soon about that. And just to kind of go through what these look like. So first, this is a kilometer deep hole. So it's 10 football fields deep, about 9 inches across. And this is kind of a schematic and sort of the details of what the anatomy of this looks like. So there's a borehole that goes through this basin filling sediment into this upper fractured accretionary prism. This is a schematic stratigraphic column of what that looks like. And then this is a schematic of the borehole installation. It's obviously not totally to scale because otherwise you couldn't see anything in the width dimension. What I'll be talking about is a pore pressure sensor that we've placed down here at the bottom of the hole. It's in communication with the formation, and I'll talk about how that works in just a second. And then it transmits signals up a hydraulic tube to sensors, to electronics that we have up top. So one of the real advantages to using fluid pressure sensing as a geodetic tool is that you don't have electronics in hard-to-get places where it's dangerous for them, right? We're not putting electronics down the bottom of the hole and hoping that they work. We're putting something pretty stupid at the bottom of the hole, a piece of steel with holes in it. And then the only thing that comes up is a tube made of steel, and all of the electronics are in a place where if we needed to, we could go down with a submersible and we could replace them or access them. All right. And again, sort of in more real life, this is again a schematic of that borehole observatory, and here's some photos of the different components, just so you can get a sense for what they look like. So this is that wellhead again, so this is a group of us working on testing the valves for those hydraulic tubing that goes down. There are a bunch of other instruments also in here, including a thermistor string and a seismometer and a strain meter, and so there's also some data cables here and power cables. There's a packer that's used to seal off the borehole because if we want to measure pressure down here, we don't want it to be connected to the ocean. We want it to be sealed off. The screens are my favorite part because they're so low tech. These are basically water well screens. They're 1-inch diameter screened stainless steel. So this is the business end of this thing down here where we're actually in communication with waters in the formation. And then this is a platform that goes up top here where a submarine can land to work on the wellhead. And for those of you who know her, you can recognize Laura Wallace here because of her hairdo. This is just, again, sort of like give you a sense of the scale of these things. So this is the wellhead, and we're actually obviously on the ship before it's deployed, testing the valves and testing the pressure loggers and programming them to start measuring. And I don't want to go into too much detail to show you each of these, one at a time, but just to again give a bit of a flavor for it. So this is a second site where we installed things, and so what does the anatomy of this one look like? It's slightly different. So here we drilled a 500 plus meter hole, and then in this case we actually have slots or screens in the steel casing, so they provide access to the formation outside of the steel tube. And then temporarily, and for the data that most of the data I'm going to show you, rather than install and cement in a complicated set of instruments that included the strain and seismometer and all these other instruments, we didn't have time or money to do it at the time that this was drilled in 2009, 2010. So we actually left the hole and we suspended it with what we call the smart plug. And it's called the smart plug because it's basically a mechanically set plug, but then we put instruments on the bottom of it, and that made it smart. So instead of just a plug, it's a smart plug. We went back a few years later, pulled it out, replaced it with a new one that had more instruments on it. We call that the Genius plug. And then after that, we went back and installed the full-blown observatory with the many components. But so here we're monitoring in what we believe to be a permeable formation. It's sort of a fractured fault zone, but it's isolated from the seafloor. So it's kind of like a pod of material that can transmit fluids and signal into this space pretty easily, but it's isolated from the ocean because it's capped by low permeability rocks. And sort of, again, in real life, just to get a sense for the scale of this is kind of what it looks like. So this element right here, which is about 2 meters long, is actually the packer. So it's made of a rubber, and by rotating on the drill string, you literally squeeze it against the borehole wall by scrunching it up. So it's kind of like, almost like a cork in a way. And then the instrument package doesn't look very exciting. It's right here, because it's just in a pressure casing, but it has a port looking downward and a port looking upward to measure the fluid pressures. Upward to get a reference of what the ocean pressure is doing for the tides and oceanographic signals, and downward for the formation. And I should mention it says happy on the side of this because if you're the co-chief scientist, you get to paint it. And it needs to be painted so that when you're down there trying to put it back in the hole, you can see it underwater in the dark. So it's this marine grade fluorescent paint. The other side of this is anniversary, because this happened to be installed on a day when I was on a 2-month-long cruise and not home for my 5th wedding anniversary. So I took pictures happy on one side, anniversary on the other side, and that was a present that I sent home. And I will let you guess as to whether you think that went over well or not. You don't have to guess. Okay. And then just really quickly, right again, there's this third site that I'll mention a little bit. It's really just in the hanging wall. It's not crossing the fault, but the idea is this is a geodetic tool because it's monitoring in its critical location really close to the trench, and also in very close proximity to the fault itself, which is a little different than these because they're hanging above it by a few kilometers. And in fact, I'll show you how sensitive this particular guy is to anything that happens on the fault. And just to, again, I don't want to kind of belabor this too much, but it's a really impressive set of operations. And so, you think about going out, and particularly folks who have been on a drilling cruise to sample for paleoceanography or to sample gas hydrates, which has its own challenges and engineering complexities. To install one of these borehole observatory systems, this is the number of steps that we had to do. This is actually from offshore New Zealand, work that Laura Wallace and I were involved with in 2018. So, it's not exactly these steps, but the idea is it's many events in terms of drill a hole, pull the pipe back out, put something in the hole, secure it, pull the pipe back out, re-enter that hole again to drill it out a little deeper or to cement something in. And so it's just a real ballet and kind of a logic puzzle of ordering. And in this case, there's something like 13 steps. They're not always this complicated, but in terms of where some of the really interesting data have come from, and if you're interested, I'd be happy to chat with folks later or, much later, not even today, because I live here. Off of northern Japan, as part of what's called the J-FAST expedition, there was an effort to go out and try to catch the frictional heat from that giant Tohoku earthquake soon enough after it happened to try to measure what is the co-seismic friction from that 50 meters worth of slip that occurred over a few minutes in 2011. And that was actually quite successful. To do that, though, you can't just drill a hole and measure because there's all of the perturbation from drilling in terms of the temperature. So you have to put instruments in and then somehow get them back or get the data back. So this was done in 2012. And then more recently, I'm not going to show you data from this, but we're going back out over just after spring break this year to collect the data from a series of borehole observatories similar to those that I'm going to show you data from today that were installed off of New Zealand. As an outreach effort, we actually had a contest where high school students in New Zealand could come up with names for these. And so they came up with Te Mate Kite, which means to see into the future in Maori. And then the other one is Athena, which actually was it is the protector goddess in Greece. Okay, and again, right, there's all this technology, but you still need like people out there on a drill ship doing things that are hard. So, it's still kind of part of it is old-fashioned, and that to me is right. Everybody's invested, and then this folks may have seen before, but also we generally try to be kind to wildlife, but you just can't predict some things. I mean, can you imagine, right? What are the chances in the open ocean in 3 dimensions that a 9-inch diameter pipe is going to be in your way if you're a squid swimming along? Right? So you can imagine why he or she inked themselves. Okay, so what do the data look like from these things? This is actually an example of some of the data from, in this case, the red is the sea floor, and the blue is the formation pressure below. And so, of course, the signal that we see in the pressures is dominated by the tides, by the ocean tides, right? So this is just ocean tides. It's measured at a reference pressure gauge at the seafloor. And then that's basically translated elastically into the formation. And so it's damped, and the reason it's damped in this case is primarily because the framework of rock is able to support some fraction of that load, and the fluids that we're measuring, the pressure of the fluids, is supporting the fraction of that load. And that partitioning of load means that this is damped, in this case, by about 70%, or to about 70% of the initial signal. But the cool thing is that because we're measuring a reference pressure, if we know the ratio of these, essentially the loading efficiency, we can use this reference pressure as kind of a brute force way, much like is done in water wells on land. If you're measuring the atmospheric correction, you can subtract that off. And so when you do that, you'll note the scale here is about 10 kilopascals. That's about a meter of water height, which is what you expect in the open ocean for the tidal amplitude. We can start to see other things besides oceanographic signals. And so this is now pressure. Note the scale here. This is far, far smaller. It's on the order of 1% or less of the ocean tidal signal. And this is an example of a medium-sized earthquake that occurred regionally. I think it's a 5-class earthquake. You can see there's this sort of quasi-seismogram from the earthquake that's just from essentially a hydrophone is the pressure. And then you can see there's a shift in the pressure that's pretty subtle that occurred where the pressure dropped after the earthquake that's related to some kind of dilation in the rock. So that's kind of the resolution that we have. In using these instruments as a geodetic tool, we want to do that a little more quantitatively than just, oh, the pressure went up, or oh, the pressure went down. So the way we do that is we think about, first let's just think about the sign of that. So you can imagine that if this is sort of like our pressure monitoring bulb in the formation, if the formation gets compressed, if it's undergoing contractional strain, what happens to the pressure? It goes up, right? It's being squeezed. On the other hand, if the formation is dilating, then it will pull on things, and we'd measure a lower pressure in our bulb. And so that's the idea. Poor pressure in the formation is ideal, particularly, it's not great for really fast strains or really high frequency, and that's because in order to measure it, you need to move fluid from the formation into your sensor, and that takes time. But it's really well suited and very stable for sort of longer term small deformations, like slow earthquakes or tectonic strains that are not earthquakes. So we can come up with a quantitative way to map between the pressure change and actual strain in the rock a couple ways. One way is theoretically using poroelastic characterization of the rock. So that's what's shown here. On the y-axis is a pressure strain coefficient. So this is how we turn. Right? If we want to use this for geodesy, we can't just say the pressure went up or down by a certain amount. We want to know how much the rock strained, and that's what we care about from the tectonic perspective. So that's on the y-axis is the sort of how the conversion goes. It's how many kilopascals correspond to 1 microstrain, and that depends on the compressibility of the material and also on its porosity. So these curves are for different porosities. So we have laboratory measurements of the compressibility of the material, sort of these bars here, and then the porosity in the screened intervals is sort of bounded by these 2 darker, bolder lines here. And so we end up with a pressure strain conversion that is on the order of 6-ish kilopascals per microstrain. Okay, so that's great. But that's all kind of theoretical and relies on these small-scale laboratory experiments. One might question their applicability to the real world in these maybe imperfect borehole systems. So the other way that we can do this, we got really lucky that there was this magnitude 6 earthquake that took place while we were out there, and we kind of knew about it, and we had the instruments in place. It provides a field calibration, which is, again, really wasn't our plan. It's kind of lucky. But it's so well instrumented that we have incredibly good constraints on where and how much that event slipped in the subsurface. So we can imagine plugging that into a model for how much would that strain the rock around it, and compare that to what we measure. So I'm going to show you kind of how that worked. So in particular, we have all of these seafloor sensors, and a magnitude 6 earthquake has enough slip that it showed up not just in the borehole observatories, but also in all of these pressure sensors that register changes in ocean depth, basically, in pressure, because they got dropped down or they got lifted up. And that's sort of what's shown here. This is work that Laura Wallace did. We actually did this analysis on the boat while we were coming back into shore, so that down arrows are where things subsided and up arrows are where things lifted up. And so that allows one to come up with a finite fault model. And then the other really cool thing is that all those pressure sensors also registered this sort of micro tsunami, centimeter scale tsunami that washed over. And so there's a tsunami waveform inversion for a magnitude 6 earthquake offshore, which I think may be like the only time this has ever been done for such a small earthquake. But in combination, it means we have really high confidence in where this slipped and how much it slipped, right? Okay. And so this is the response, and both boreholes went into compression. So they both registered pressure increases associated with this magnitude 6 earthquake. And essentially, what we find is that if we plug in that known earthquake source, we predict from that elastic response from that earthquake, what should the strain be at the two boreholes? It's 0.5 and 0.2 microstrains. And if we measure the pressure in the borehole and use the pressure strain conversion from the theory, we get something darn close to that. And so this is a really nice kind of field calibration that we think we can use to say we know how to turn pressure into strain. And that's really a key here. Without that, we can only do something sort of qualitatively or at best in relative terms from one event to the next. So what are some of the other cool things that we see? Okay, so this is kind of getting to the heart of it. In these borehole pressure records, and I should back up and just say, when we installed these, we were not thinking, oh, we're going to go find slow slip events. We were thinking, we're monitoring in these boreholes that are kind of spanning the edge of the big earthquake slip. And so there will be interesting things happening there. Maybe we'll be able to see it if a big earthquake happens. Maybe we'll be able to monitor whether there's locking. And so it was a little bit of a surprise to us that actually what we found were these recurring, spontaneous pressure transients that were synchronous at the two boreholes that are 11 kilometers apart. And so what's shown here is a few examples of that. So this is now detided. There's still some residual tide in here that we can't get rid of because our sampling rate wasn't high enough to get the phase shift exactly right. So it looks like it's tidal, but it's actually less than 1% of the tidal amplitude, and that's about as well as we can clean up the data. But hopefully you can still see, like, this isn't a case where whatever happened at this time caused this to go into some kind of dilation and this to go into some kind of compression. This event is a little more complicated, and I'm calling it an event, but for now, if you don't believe me that they're slow slip events, you can just say it's a strain event, right? So we see cases of mixed sign. We see cases where they're mixed sign, but then they become the same sign later on in time. Some of them are, I said they're spontaneous, some are triggered. So this is after the Tohoku earthquake. There's a 2-day period that's not just the aftershocks, but there's actually kind of slow deformation or strain that's happening after in between the aftershocks. And then here's another kind of small one that's mixed sign. So kind of an interesting array of events, and for now I'll call them strain events. But if we think about like how we can get these signals, again, just a thought experiment to start. So let's imagine the first part of this event to 2016. This is the complicated one where I have to mask the second half of it, right? So here's the first half of it. To get this guy to go into extension and this to go into compression, right? Pressure's going up. You can imagine one plausible explanation for that might be if there's slip along the master detachment down below or on the plate interface that has a centroid somewhere between the two sites. So that puts you in an extensional lobe here and a compressional lobe here. Well, then how can you get this part of the event? Well, one possibility is maybe the event migrated, right? And if the event migrates, it would place both of these boreholes into extension and then it would place this region into compression, which I can say with confidence and luckily, because we didn't have anything to test my hypothesis at the time that this event happened. But if we did, we would have expected that the borehole here, which had not yet been drilled and installed, would have registered compression. So that's the kind of working hypothesis for this particular event, that it's a slow slip event on the plate interface. One of the pieces of corroborating evidence that sort of, for me, is very convincing is that there's a concurrent migrating tremor swarm at the time of this event. And I say concurrent, it's quasi-concurrent. So let's just start. This is a map view, and what's shown here, the colors don't really mean anything. They're depths, but they're pretty poorly constrained because we don't have a great velocity model out here. The horizontal locations are actually much better because they're detected. This tremor is detected by this network of 24 seismometers with really good azimuthal coverage in the near field. So there's this tremor swarm, and a couple things are interesting about it. One thing that's interesting about it is that you'll notice that it occurs primarily trenchward or southeast of both drill sites, right? So it's in this region where if this is slipping, then when this is activated, you would expect it's pulling on both of these sites and putting them into extension. And lo and behold, the timing of the tremor is exactly, in fact, it turns on in this region exactly when both sites go into extension. So that's totally consistent with the idea that the tremor maps onto this portion of the plate interface slipping at that time, and that's consistent with being in the extensional lobe for both of the boreholes. And then the other thing that's interesting is that, and what's shown on the top here is this is distance from the trench along sort of these bars here as marked. And then this is time. And hopefully you can see there's some slope to this. It's actually, the tremor swarm is migrating trenchward. And so that's also consistent with this idea of the whole thing migrating trenchward, right? If the tremor's migrating trenchward, it kind of makes sense that the slip event might also be. So, so that's interesting in itself as sort of corroborating evidence that this is slip on the plate interface. The other thing that's really interesting about it is there are very few studies where people have been able to tease apart and understand the relationship between tremor and these slow slip events. And so there's maybe less so now, but certainly up to maybe a year or two ago, it's quite controversial whether the slow slip was just a manifestation of lots of tremor and the slip was a byproduct, or if the slip is happening and the tremor is the byproduct, not driving the slip, but more like bristles on a brush, just being activated as the slip happens. And our data pretty clearly show it's got to be the latter. And there are a couple of lines of evidence. One is we have slip where there's no tremor, and then we have slip that's related to tremor. So there's sometimes slip that doesn't activate tremor. It's hard to then think that the tremor's making it slip. And then the other kind of nail in the coffin, so to speak, is that the total moment of the tremor is minuscule compared to the total moment of the slip event. 3 orders of magnitude smaller. Okay, and here's an example of just a triggered event. This is actually triggered by the Kumamoto earthquake. So this is 2016 earthquake that actually is a strike slip event way down here onshore. But again, it activated the fault, it caused extension. So again, we think that it means that it's the outer part of the system that's slipping nearest the trench, and super energetic 700 plus tremor events that again exhibit a migration toward the trench. As I mentioned, not all of these events activate tremor. So here's an example of a pretty silent one. It's a little smaller, but it wasn't accompanied by tremor, maybe a few little blebs of tremor, and these regions are kind of persistently active, almost like little sticky spots maybe on the fault. Okay, so again, there's sort of a lot of evidence, and I think we're pretty convinced that these are slip events, these slow slip events on the plate interface. So now this is actually work that Josh is doing as part of his PhD, is to say, all right, well now we want to do a little bit better job of saying, well, where and how much slip? And the data, although we only have 2, or for some of these events now 3 data points if you include the third observatory, so N is small. We don't have like hundreds of data points to do an inversion, but we have enough data to start to say something reasonable. And so that's what I'm going to talk about for a minute here. To do this, we don't want to use really simple elastic models where you have everything in a uniform half space and you just slip and see what happened. There are great solutions for that. They're terrible for this because the properties of the rock change by orders of magnitude as you go from very soft material near the surface to more rigid material at depth. So you need to account for the spatial variation in properties and those gradients. And that allows us to say something about the locus and magnitude of slip. And so I'll just show you essentially the results of this work. And so this is a busy slide. I'll take a minute, and I apologize for how small the text is. Let's start here. This is a 2015 event that we've kind of looked at already. So because the data, although we only have two observation points, the data are clean enough that we can break it up into sub-events on the order of a few days long each, and ask the question, for each 2-day period, pressure changed here by a certain amount, pressure changed here by a certain amount, can we say something about where the slip would have to be to get that ratio of slip at those two places? So the relative magnitudes of strain at 2, or in some cases 3 holes, provides some triangulation on the location. And we do this using Green's functions that are generated in PyLith, which is a 2-dimensional elastic model that accounts for this heterogeneity. And then we can get amplitude once we have a location. Then we say, okay, the ratio of strains tells us it has to be at a particular spot as a best fit. So it's kind of optimizing, but it's not truly an inversion. And then we can say, okay, now to get the size of the pressure change, not the relative values, but the actual absolute size, how much slip needed to happen. And so it's sort of a 2-step process. And the result of that, I should probably highlight this more, but it's shown in this teeny tiny plot on the bottom. So this is time on the x-axis, and this is location on the y-axis. And so you can see both in this 2015 event and this 2020 event, there's very clearly a migration of this best fitting slip patch from far away from the trench toward the trench. That's sort of the first takeaway here. And the second is that the colors map to a sort of a heat map of how much slip. And so you're talking about the red is about a centimeter of slip, and the blues are a millimeter-ish of slip. And so the slip is, first of all, we're able to detect pretty tiny slip, but second of all, it's petering out as you go towards the trench in a broad sense. And so this is something that we're able to do with the kind of data that we have. Another thing that's enabled by this kind of data is not just to look at the migration of slip in detail, but then to start to ask the question, how does it look relative to the tremor? And so what's shown here is now putting that together in a slightly different way. These black dots are for the 2015 event, showing that migration. And this is the centroid is shown as the black circle, and then the error bars show the extent of a 20-kilometer wide patch. So they're basically, this is sort of the width of the patch, if you want to think of it that way, in kilometers from the trench as a function of date. And so this is the migration of the event. It's really what I just showed you in those little tiny colored dots before, but now I've flipped it around on you. And then the red dots are the tremor in map view. And so again, it's not like it's beautiful and perfectly clean, but hopefully you can see that the slip event does seem to kind of dovetail right into the tremor. And then this is the migration of the tremor. There's sort of a branch of a smaller number of tremor events that are doing something a little different, but there's certainly some degree of migration here. And the rate, if you want to interpret this as a rate of migration, is actually not that different than the rate of migration we interpret for the slip on the slip patch. So we're kind of now trying to work on, dig a little deeper even and ask the question, well, does it make sense if we're now to look at stress changes associated with reaching this point? You'd expect to have the highest stress concentrations near the tip of the fault that just moved, and maybe that's something that can explain the activation of that tremor. And so this is, again, sort of work to be done. The other thing that's interesting, and I'll just kind of briefly point it out, is that people also argue a lot in the seismology and slow earthquake community about whether tremor and the amount of slip are related. Intuitively, it makes sense, right? Bigger slip, more slip, you should get more active tremor, bigger tremors. But again, there are very few data sets that allow this kind of analysis. And so that's what's done here. Slip for each of the 2-day sub-event windows on the x-axis, and then the cumulative magnitude. So it's basically a tremor count that's scaled by the tremor magnitude or tremor energy on the y-axis. The open circles are for when slip is 20 kilometers or closer to the trench, and the black are when slip is farther back than that and away from the trench. And so a very clear thing that shows up here is the same thing that I've been saying already, is that when the fault is slipping farther back from the trench, there's no tremor. When the fault is slipping nearer the trench, and maybe there's a relationship between how much tremor energy is released and the amount of slip, but it's not perfect, but there's some hint of a positive relationship anyway. Okay. So just another sort of point to make here is these are expensive instruments. They're not the kind of thing you can put everywhere. Right? They're expensive both in terms of the actual equipment, in terms of the infrastructure it takes to put them in, and then to get the data back requires either taking ships out and plugging into them or putting a cable in, which is really expensive. But their value is really high, especially if they're strategically placed and you can only do a handful of them. And so that's kind of what's shown here, just as an example. for a lot of the community at the vanguard of offshore geodesy, the thing that's really catching on and is incredibly useful is seafloor pressure gauges. And this is because it tells you if you've had vertical displacement of the seafloor. If you can correct out the oceanographic signals, you can resolve maybe a centimeter or two of uplift or downdropping. It's really hard to do something related to, say, long term or to tectonic strain accumulation. But if you want to know what happens in an event over the course of a week or a month, they're pretty powerful for that. And they've been used in places like New Zealand and offshore the South American coast. And so what's shown here is what you'd be able to detect with those kinds of cutting-edge, top-shelf instruments in today's world in the face of oceanographic noise. And so this is for the geometry offshore Japan, just as an example, right? Because the details here do depend a little bit on exactly where things are. And basically what this tells us is that it kind of doesn't matter where you put your slip, but for wherever you put your slip, you might be able to pick up the event if it slips 10 centimeters-ish. That's a pretty big event. That's what happens off of New Zealand, and that's why these work off of New Zealand, is they're really large, slow slip events. Borehole sensors get you about an order of magnitude better resolution, and this is because of the fact that they're in a low noise environment in terms of oceanographic noise, and or you can subtract off the oceanographic noise. And secondly, because there's an amplification factor when you're looking at the volumetric strain of the rock as opposed to just the vertical displacement. So those two things combined actually allow us to get a much, much higher precision and much, much better detection limit, to the point where we can see millimeter scale slip in 4 kilometers of water depth, 60 kilometers from the coast, on a fault that's buried. Kind of insane. All right. So just to put this together in terms of the sort of time scale, and then if I have time, I'm going to launch into a few other little things, but if not, that's fine too. So what's shown here is just sort of a 6-year record, which now, again, Josh has extended to a decadal record, and he's working that up to bring it all the way up to 2023. But what's shown here is amplitude of the event on the y-axis in terms of its strain or pressure signal, and then a timeline. And then the symbols here just are coded for whether things are both extensional, both compressional and solid, or mixed sign, which tells us a little bit about the position of the event. And so the idea here, right, is it's pretty clear that it's kind of on the order of about every year is one of these slipping clutch kind of slow earthquake events in the outer part of the subduction zone. Some of them are a little, put both boreholes into compression, so they're a little bit further back. Some of them are sort of mixed signs, so we interpret that to be in between the two. Some of them are extending both sides, so we interpret that to be farther out near the trench. But in total, if we sum up those displacements, what we come up with is sort of every year to year and a half we have these slip events. What's interesting is we can say something about how fast the slip is occurring, which is really interesting from the physics of faulting perspective and what the rheology of the fault must be to allow that to happen. And these slip rates of kind of fractions of a centimeter to maybe a couple centimeters a day is actually about what people are seeing for comparable slow slip events in other places, which is interesting and again suggests maybe there's some kind of universality to the physics behind this. That's again this window into fault rheology. From a hazards perspective, one of the things that's really, I think, really important result of this work is that the amount of slip in these slow events that we sum ends up being something like 30 to 50% of the plate convergence. And I put 50 here rather than 30 because with our refined models, it looks like that number's higher. So I think it's closer to 50%. So that means that that's at least 50% that's not locking, right? So that's important for thinking about hazards, not just for earthquake slip to the trench, but also tsunamogenesis. And I'll just say this is also consistent with long time scale geodetic data sets that have been collected. So this is now Japanese Coast Guard data. This is Yokota et al. Published in 2016. There was a more recent paper in 2020. And this is a coupling map. So again, where it's red, it's fully locked. Where it's blue, it's partly locked. And we kind of sit in this yellow zone. Their grid is so coarse, they have 24 sites over the entire coast of Japan, right? So it's not super high resolution, but we're kind of parked in this zone that's sort of what they call partially coupled. So it's consistent, the idea that we're releasing on order of 50% of what might be accumulated tectonically over with plate motion is at least broadly consistent with the decadal timescale where it's not going to see those year-to-year events. That's basically, to this data set, that's creeping, right? And what they're seeing is whatever's left over. And so for them, what's left over is something between 0 and 50%, which is totally makes sense. Of course, what does this mean in the broader picture of hazards? Well, you could cut it two ways, and so there's still, I think the jury is still out. I think it'd be dangerous to say, oh, well, okay, so it's only 50% locked out there at worst. It's lower tsunami hazard. On the other hand, we know that this slips when it's triggered by distant shaking from like the Kumamoto earthquake, which is a strike slip 7.3 earthquake a few hundred kilometers away. So you could then argue, well, maybe it's perched in near failure, and it doesn't really matter if it's locked or not, because if you kick it, it will still fail. And so I think we're still struggling with that and sort of unwilling to take a side when it comes to saying something definitive about hazards. Okay. And I do have just a couple quick minutes. I'm just going to say a few quick words about what else we know about the habitat of these events, because this is some neat stuff that's also ongoing in my group, but also gets to this question of, okay, so this is the hazard side of it, but now what else can we tell you about what we're learning about fault physics and earthquake physics from the occurrence of these events? And so this is a little bit of a glimpse into one particular, these are the optimized models. So these are, again, those colored dots I showed you migrating from the models, the optimizations that Josh Edgington has done, shown in a little bit different way here. So now we're looking at the amount of slip as a function of position over the course of the event. And so this is that 2015 event. So it starts about 35 kilometers from the trench in the dark blue, and then these are timelines of the event. So you can see the migration toward the trench, and then you can see the total final slip distribution is just the sum of all these increments, is sort of the final position is the top curve here after the event's over. So a couple cool things come out of this, right? And here's the tremor. One is that slip clearly peters off towards the trench. There's sort of a zone that's pretty clearly the zone where most of the slip occurred. The 2020 event is smaller and less well resolved, but shows a kind of similar behavior. And the zone where most of the slip happens in most of these events is spatially correlated with the zone that we've previously identified from low seismic wave velocities as being a zone of overpressure under compaction. And so it's consistent with mechanistic ideas people have about how you could get these things to be slow, is that there's low stress and the rock is really weak. So that's something we do see, or we think we see. And again, the detail here is really this next step that Josh is working on with these better models. We also had a paper out last year that got at the stress state in the system using drilling data. And so that's what's shown here is now the stress state deep into the hanging wall, about 3 kilometers and change deep into the zone just above where a lot of this action is very interestingly very far from thrust failure conditions. So that's what's shown here. This is stress versus depth. The overburden is the black curve. This brown curve is what you'd expect if it's at a state of thrust faulting failure, which the subduction zone is kind of a giant thrust fault, so you'd like to think that's where you are. And the blue is the minimum stress. This pinkish zone is the maximum horizontal stress. And so the upshot here is that even down to sort of the heart of the hanging wall, all the stresses are similar to each other. The difference in stress that might drive faulting is really low. So again, it's consistent with the rock being really weak, not being stressed very much. And so something has to change as you get towards the fault in order for it to move as a thrust fault, but that might not have to be a lot. And so, again, it's not super puzzling, but it's consistent with ideas that the community has about these events being related to low stress, elevated pressure that keeps the rock weak. And then I'm not going to go into crazy detail here because of the time, but just to say, we've also been able to do rock mechanics experiments in our lab here, and previous to this at Penn State, and folks at the University of Bremen are doing this, lots of other institutions. We actually, because of all the drilling here, we have rock samples of the faults that we think, okay, at very shallow depth, but sort of the tip of the faults that are actually participating in these slow events. So they're the best materials we have in terms of what we think the fault rocks are along this fault. And if we test them in the laboratory by doing shearing experiments, one of the things that we can do is measure whether they get stronger or weaker as they slide faster. And so this is a behavior called velocity dependence of friction. And the idea is that if you slide something faster and it gets weaker, then it's capable of going unstable. You kick it, slide a little bit faster, it's perturbed. Once it goes faster, it's a little weaker. Well, that means it can go even faster because there's all this energy in the system that's trying to get it to slide. And so it gets less and less and less resistance the faster it tries to slide. It can become runaway. The alternative is if it gets stronger as you try to go faster. Velocity strengthening behavior. In that case, it behaves more like a damper or viscous behavior, right? So you try to slide it faster and it resists. You can't get going and have something unstable. So we do these kinds of measurements in the lab. And so what's shown here is just the result of that for these rocks from this fault that participates in these slow earthquakes. And so what's shown here is this parameter A minus B, which is the extent of whether it's getting stronger as you go faster, which is above 0, or weaker as you go faster, which is below 0. So there's a very faint dashed line here that divides these two fields. Everything down here is potentially unstable because it could run away under the right conditions. Everything up here should never go unstable because it gets stronger if it goes faster. And what we see is that these rocks, for certain stress conditions, could host something or nucleate something unstable, but only when they're going slow. And as you speed them up, they actually become rate strengthening, or more like a viscous behavior. And so it's not just a single value of whether it gets stronger or weaker as you try to slide faster, but it depends on the velocity. And so you can imagine, and this is not just for these rocks, but you can put it in the compilation of rocks from subduction zones or exhumed subduction zones in the Chemin Belt here. And there's sort of a broad trend here that suggests that you could, in these kinds of rocks, they exhibit a frictional rheology that allows them to nucleate something slow, but not get fast, because as they go faster, they'll damp that. They'll suppress that fast motion. So again, it's really consistent with the idea of having something that could be unstable, but stay slow. And so we have the environmental conditions of pressure and stress, and the rock material properties are all probably ingredients here, but they're all consistent with the behavior we're seeing. And I'm going to leave it there. I'll just leave the summary up because I think I've said all these things already. And yeah, happy to take some questions.